LD kind of low, huh?
One thing that people are hear quite often, but they're not really familiar with, is the idea of a scientific theory. A lot of times you hear people saying, "Oh, that's just a theory," but what they really mean is, in science terms, hypothesis. A hypothesis is something that may not be very well supported. A theory in science, though, is actually very well supported. Generally, a theory doesn't get to be considered a theory unless there is essentially no evidence against it. So theory in science is actually a very high ranking of information. And theories are much broader than laws. Theories are a sort of a broad historical framework of knowledge and it takes in all of the principles and facts known about a particular area of science. Okay, and a scientific theory is one way that it's different from a law is that theories are larger and more complicated than laws, but also another difference is that theories explain why something happens. Not just what happens. So a law describes what happens, but it doesn't explain why. A theory explains not only what happens, but it also explains why. So one theory would be atomic theory. That is the theory about the structure of the atom. It contains lots of calculations about where the electrons are and how we know where they are or don't know where they are, as the case may be. And it encompasses a very broad range of, of things. Evolution. It explains why animals evolve, not just that they do. Or the Big Bang Theory. It explains the origin of the universe, why it happened, not just what happened. Okay? So that's some background on scientific theories and basically the scientific method. And since that's the basis of all science, we really needed to have a look at that before we look at science in more details. Okay, and as I said at in the organizational part there at the beginning, the first part of the course is a math review based on the math packet, which you'll find posted on Blackboard. And sort of as a lead up to that, we need to first establish some of the stuff that we're going to be dealing with in the math packet, which is things like measurements. So what is measurement, first of all? Measurement is a comparison of a physical quantity to some well-defined reference. So if you take a ruler and measure a sheet of paper and you find out that the paper is 8.5 inches wide, that you're basically comparing the width of the paper to that well-known reference, which is the inch. Okay, so essentially the reference would be a unit. Or any other thing that's well-defined and agreed upon. But normally it would be a unit, like an inch. And generally what we measure are physical properties. Physical properties are properties that can be measured without changing the object or the substance. So something like, I don't know, weight would be a physical property. You can weigh something without changing the identity of what that something is. Color, you can look at something and see what color it is without changing what the substance is. That would be as opposed to chemical properties like, I don't know, flammability. To find out whether something's flammable, you have to set it on fire. And once it starts burning, it actually, that is a chemical reaction, and it is being transformed into other substances as it burns. So that would be a chemical property. And when it comes right down to it, what a measurement is a number combined with a unit. So essentially, the unit is the reference, and the number tells you how many of those reference items correspond to the item that you're trying to measure. And fact is that a number without a unit is pretty meaningless, really, when you think about it, because you can't tell what it is. And lots of times in lab classes, people will write down data from measurements they do in the lab, and they'll write down the number, but they won't write the unit. And they'll come back to it later when they're trying to write up the lab report, and they'll have no idea what that number means because they didn't write any units after it. They don't know if it's a mass or a volume or what. Okay. So there are four fundamental properties of nature that we tend to want to be able to measure. And one of those would be length. And remember, the length, some of these units can actually lead to what are known as derived units or derived measurements. So length, if you take length times width, width is just length seen from a different angle, basically. So length units can also lead to area or volume. So length times width times height is volume. And length and width and height are all measured in length units. So there are types of length. And yeah, length also leads to volume. There's also mass and length, volume and mass can lead to density. So that's another type of measurement. And then there's time. And electrical charge. And basically all other physical properties are described from these four, all other measurable physical properties anyway. So derived properties are things like I was just mentioning up above, area and volume and density. Those are all derived properties because they're derived from one of these four main properties that I listed originally. So area is the extent of a surface. And it's generally listed as being length times width. But width is really a type of length. And so the units would be length units squared. Oops, there you go. So think of any unit of length, and if you square that, then you have an area. So like square feet or square inches or square meters, square miles, those are all types of area. Okay, so square meters, square feet, square inches. There is a special unit for area, which is acres. And acres corresponds to a certain number of square feet. I forget the exact number, but we could look it up. But you know, it's the one case where you have a unit that is a unit of area, and it has a special name that's not length units squared. We can look at an example of area. Say you've got a small black box theater, and the space measures 30 feet long, or 30 feet wide and 60 feet long. So the area would be length times width. That's 60 feet times 30 feet. And 60 times 30 is 1,800. And for the units, when you're multiplying and dividing, you treat the units as if they were a number. So feet times feet would be feet to the second power, just like, say, 2 times 2 is 2 to the second power. And that would be 1,800 square feet. Feet to the second power is usually said as square feet. Another derived unit would be volume. And volume is really just a measurement of the amount of space occupied by something. And in terms of calculation, volume would normally be length times width times height. But width and height are just other types of length. And we just use different words to distinguish one measurement from another when we've got something like a box. And so the units would be length units to the third power, or length units cubed. And some examples of those would be, say, cubic meters, cubic feet, cubic inches. But also there are some special units for volume, more than there are for area. Special units for volume would include liters and related units like milliliters, or gallons and related units like ounces. So those are special units. They're volumes, but they are not explicitly length units to the third power. An example of a volume calculation would be, suppose that same theater space is 60 feet long and 30 feet wide and 16 feet high. Well, the volume would be length times width times height, and that would be 60 feet times 30 feet times 16 feet. And that would be 28,800 cubic feet, feet to the third power, in other words. Okay, so that feet to the third power, cubic feet, that is a measurement of volume. In order to do measurements, we need units, of course, as I already said. And units are usually part of what's known as a measuring system. A measuring system can be thought of as just a set of base units that a governing body agrees upon. There are various governing bodies to govern various types of measurement. So we also have the English system of measurement. That's the system that we use in the United States. And some of the standard units for the English system of measurement would be inches, feet, miles for length. For volume, you could have length units squared, or sorry, cubed, or you can also have gallons or ounces for volume. And for weight, we have pounds and again ounces. And those are sort of the standard units in the English system. Then we have the metric system. The metric system is an international system of measurement that's used essentially by the entire planet except the United States. And the metric system of measurement is, like I said, very well known everywhere except here. There are all kinds of units that you can use for length and volume and weight or mass in the metric system. But, well, actually, let's first say the metric system is a very orderly and systematic and logical system of measurement that was established in France after the Revolution in, around 1800. And it has really stood the test of time because it was set up very deliberately with thought ahead of time about how things related to each other. The English system goes way, way back into the Middle Ages and some parts of it even earlier. And they used things that made sense for measurement at the time, like the inch was the distance between the end of your thumb and the first knuckle, and the foot was supposedly a length of the king's foot, and things like that. But those things were not standard measurements. Different kings have different size feet. Different people have different distances from the end of their thumb to the first knuckle. So people needed a more systematic type of measurement. And eventually the measurements in the English system were systematized with standard values for all of these units. Those values are governed by probably, I would imagine, the National Institutes for Standards and Technology in Washington. And I'm guessing that because the United States, like I said, is the only country that really cares about the English system of measurement anymore. On the other hand, the metric system was set up with very deliberate and thought out relationships between the different units. In the English system, you have relationships between units that were often based on God knows what, like 12 inches per foot and 5,280 feet per mile. What's with that? I mean, where did they come up with those numbers? With the metric system, everything is based on factors of 10. So like relationships between two units will usually be something like 10 or 100 or 1,000 or a million maybe, or 1/10 or 1/1000th or something like that. You don't get weird numbers like 12 and 36 and 5,280. So that's an advantage to the metric system. It's also an advantage that they based the system on things that were readily available. Well, not maybe readily available, but things that didn't change from one place to another. So the meter was based on 1/10,000,000th of the distance from the North Pole to the equator, going along the surface of the Earth. That is a value that doesn't change from time to time, so it was a constant value. They also arranged things to work out very conveniently. So for instance, a volume of 1 cubic centimeter happens to be the same thing as 1 milliliter. 1 milliliter of water happens to have a mass of 1 gram, which is one of the units of mass in the English and in the metric system. So that made things much easier to understand. The chemists and physicists use what's known as the SI unit subset of the metric system. Which stands for Système International in French. That's why it's SI instead of IS. And this gives a particular subset of the metric system where certain units are used for certain types of measurement as kind of the official unit. And that's because there are certain equations that will only work out correctly if you use certain units for certain measurements. Unfortunately, those units are not always the most convenient units to use for certain types of measurement. So we need to be able to develop skills involving unit conversion so that we can change from one unit to another. We can do the measurements in a unit that's convenient and then rely on our mathematical skills to convert that unit to another unit that we need for an equation. Okay? So I see by the clock on the wall that we're right around our time limit for this part of the video. So I'm going to stop this video now, and I will continue on with the rest of the SI system in the next part. So I'll see you in a moment.